ba 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 director. Man, what am I doing?
Hello, and welcome back to another exciting episode of Mr. Bell Physics, where today we are celebrating our 50 subscriber special. I have no idea why you guys are subscribing to the channel. It's really not that great content, but I'm doing my best, and I appreciate all the love and support that I've been getting so far. Expect videos to hopefully slowly start getting better eventually. Maybe. We'll see what happens. As a way to celebrate and as a way to finish off our Kinematics series, there's a little bonus episode to that. I wanted to show off a problem that I'd given to my accelerated physics students a few months ago that I had made that kind of stumped them at the time, walk us through how to do it to make sure we all feel good about it. My accelerated students, if they are watching this, if I had to say the Tom Brady problem, they immediately will know what I'm talking about, partially because of PTSD. But if it wasn't already clear by my alpha usually during these videos, I'm a pretty big sports fan. If it wasn't clear from the Hartford Athletic scarf up here, the New England Revolution scarf back there, as well as just various sports references I've probably made. I am a big sports fan, specifically New England sports. So I wanted to give a little bit of love to the greatest of all time, Tom Brady, with this question when we were doing projectile motion. So during Super Bowl 42, Tom Brady threw a pass 60.35 meters downfield to Randy Moss. It was broken up by defenders. It was a Hail Mary attempt to try to beat the Giants in 2007. Didn't end up working. It stayed in the air for a total time of 3.14 seconds. Part A asks, what is the maximum height that a pass reaches? Part B is, how fast does Tom Brady throw this pass? And C is, what angle does he throw this pass at? Now, if I can, with my very rudimentary editing skills, I'll include a video of the pass here.
Brady rolls, heaves, Moss downfield, broken up by Webster.
Did it work? Maybe. Who knows? Right? Maybe you just got to see the video. Maybe I'm going to get copyright striked by the NFL. Who knows? Right? Either way. So that's the pass, maybe. It was a big pass. It's, I think, the longest pass of Tom Brady's career, or longest pass attempt at least. But it presents an interesting problem for us with projectile motion. See, I've already kind of set up our table here with our variables, and as well as kind of drawn out the arc of motion here. Normally, in a projectile motion problem, we are given an initial velocity and an angle, had to break it up into the components, and figure out things like maximum height, distance, time, etc., based off of that. In this example, though, we're actually given distance and we're given time, but we're not given any information about initial velocity. So instead, we have to work backwards. So let's see how we can do that. Now, let's start off, as per usual, filling out our table to the best of our ability. Before I even read the problem, I want to fill in the things that I can immediately assume are true. So let's start with our x values. Okay, I know immediately my acceleration in the x direction is going to be 0. I know that is going to be the case for all of my kinematics problems whenever I'm dealing with projectile motion. Acceleration in the x direction is 0. My velocity does not change once the ball leaves my hand. However, I don't know any other information yet. I know for a fact that VI and VF will be equal to each other. So that's cool, I guess. But that doesn't really help me out right now. Okay? The other piece of information I know that is given to me is my distance, which is 60.35 meters. So that's all the information that we get in the x direction. Let's see the y direction now. We get really no information here, besides time, which we get for both, which I'll fill in a second. But we get acceleration due to gravity, I guess. Right? We know that's 9.8. And we know that time is 3.14 seconds. And we know that carries over for both. But that's all the information that we get so far. Okay? We specifically want to figure out how high does the ball go? We want to know how fast the ball is going when Brady throws it, and we want to know the angle. Because we want to know the angle, that tells us that we actually want to know the resultant vector of these components. So I need both VIX and VIY. But if we go to our diagram here, that immediately gives us some information that we can use. Okay? We know this time frame, this distance 1 is 60.35 meters. We know that. But we also know this is 3.14 seconds total. Which means that in order to get to our peak, we know that that's going to be half of that time. So from Brady throwing the ball to the ball getting to its absolute peak height, to the ball going from its peak height all the way back down into the hands of Randy Moss, we know for a fact that that is going to be exactly half of 3.14 seconds. So if I grab my calculator, which is on my desk over here, and I do that math out in my calculator, 3.14 divided by 2, I get 1.57 seconds. So 1.57 seconds over here, 1.57 seconds over here. Now, why do I need that number? I need that number because part A is asking for the maximum height. Basically, whatever this red line is. In order to get that height, I need to know how long it takes for the ball to get up there. You may be tempted to use 3.14 seconds, but in actuality, it only takes half the time for the ball to get all the way up. So therefore, we want to use the half time, which is 1.57. So, utilizing that, we also know V final for y in this case, at least for half of y, is going to be 0. We know that once we are up here, actually I'll use red for this, we know that once we're up here, this will equal 0 meters per second. It is no longer going to be rising or falling, right? It is steady in that specific instance. So, we know final velocity. We do not know initial velocity, which is a bit of a shame. We know time. We can also figure out distance in the x direction up to this point, but that probably won't help us too much. So, if I take a look at my formulas, okay, I'm going to omit writing them on the board. Okay, I'm going to hope that you guys have them written down from the previous part. If you don't have them written down, please go check out, I believe it will be part 4 or part 5, should both have them written down. So I'm looking at my equations here. I'm going to go through them in order here. Okay. I need to stay away from anything that has initial velocity, essentially, because I don't know it yet. Right? Either that, or I need to stay away from anything that has both initial velocity and distance. Okay? Because those are my two unknowns right now. I don't know initial velocity in the y direction. I don't know how high we end up going yet. Okay, so those are two bits of unknown information that aren't really going to do anything for us. Okay? If I can solve for either of those two pieces of information, I'm in a good spot. So, first equation, V final equals V initial plus acceleration times time. Okay, well, let's look at it. I have V final, I know that's 0. I don't have V initial, but I know acceleration is 9.8. In this case, it's going to be negative because we're going up. And I do have time. It's 1.57. So in theory, I could solve for initial velocity in the y direction here. So that's cool. If I'm looking at all these equations now, there is no equation in here that has delta x that also does not have VI. So in this case, we need to do things a little bit out of order. We need to solve part B before we can solve part A. So let's go ahead and do that. So I want my initial velocity in the y direction. So I'm going to write that right over here. So V final y is going to be 0 equals V initial y I don't know that yet. Plus my acceleration, which is going to be negative 9.8 times my time of 1.57. So, let's do this out together. Okay, making sure that that's still visible. Yeah, you guys can see that. There's a little glare there. I apologize for that glare. So, negative 9.8 times 1.57 is equal to negative 15.386. So, in other words, 0 equals VIY minus 15.386. From here, solving is rather simple. I just need to add 15.386 to both sides. Oop, if I could actually write to number 8, that would be great. Spitting bars over here, rhyming and stuff. Crazy how that works. 15.386. So those go what? And I get VI in the y direction is 15.386 meters per second. So that's really great. That's a really useful piece of information. I want to update my table immediately with that. 15.386 is my initial velocity in the y direction. Awesome. From here, I now know we're going up at 15.386 meters per second. I know how long it takes me to get up there. I know my acceleration. I know my time. I know my final velocity. I can absolutely solve for x here, and I can use pretty much any of the equations that I want. Let's see here. Let's use equation 3. So equation 3 reads delta x equals VI, which is 15.386, times time, which is 1.57, plus 1/2 negative 9.8, because that's acceleration, times time squared, 1.57 squared. So, let's simplify this. Okay, let's do it one step at a time. 15.386 times 1.57 comes out to 24.16 about. Plus 1/2 times negative 9.8 times 1.57 squared. So make sure to just get my parentheses right here. When I do that out, I get negative 12.08 about, rounding. This is still equal to delta x. So in order to get delta x, okay, my height, I combine the two. And doing that in my calculator, I get delta x is equal to 12.08 meters. Now, I'll slow down for a second, right? Just kind of walk through that again. It's important to remember that A has to be negative still here. Okay, with the final velocity that I am using, which is 0, we are slowing down. Now, in theory, my final velocity down here should be the same as my initial velocity up here. And I know that because of conservation of energy, which is something that we haven't talked about in class yet, and it's something that I have not made a video about yet. But it is true that my velocity will be identical so long as we're ignoring things like air resistance or friction or anything like that. But for our purposes here, we use the first half here, which means we had to use the negative acceleration. Remember, we're slowing down up here, so therefore this has to be negative 9.8. And speeding up down here, so this has to be positive 9.8. And make sure that you're paying attention to why your number is negative or positive there. Big, big important thing there. So that blank goes away, that becomes 12.08. All of a sudden, we're already almost done. Okay, we actually fill in this one too, it's just 0 for that first half. Okay, so long as we also change that 3.14 to 1.57, of course. So we're actually almost done already. Now, we just need to solve for initial velocity in the x direction. This is actually more straightforward than it may appear to be. We know displacement. We know time. Velocity is just displacement divided by time. Now, we'll still use our kinematic equations to do this properly and all that good stuff. Okay, sure. But it'll simplify to just displacement divided by time. So, let's see here. Right now, do we have any equations that we can use here? I'm going to have something without VI in it. The answer here is actually no. We do not have any equations that do not have VI in it. Okay, so in that case, we immediately need to start looking for equations that don't have both VI and VF. There is exactly one equation that does not have both VI and VF in it, and it is equation 3. Delta x equals VI times t plus 1/2 AT squared. So, I'm going to erase my Y math here. Okay, hopefully you already had that written down. If not, I'm sure you can rewind, because I'm sure there are plenty of frames with me with all that math behind me. And over here, I'm going to use my full time now, my 3.14. Okay? So, delta x, which I know is 60.35, equals VI, I don't know that yet, times t, 3.14. So 3.14 times, actually I'm not even going to do times, I'm just going to write VIX plus 1/2 A 0 times t 3.14 squared. So again, all I'm just doing is just plugging in my variables. I knew acceleration was 0. Okay, I know that for a fact. I don't need to worry about that. So that entire last term just goes away. Hasta la bye-bye. Which leaves me with 60.35 equals 3.14 times velocity. In order to get velocity by itself, these two are being multiplied. I divide 3.14 divided by 3.14. So VIX equals my displacement divided by my time. Shocking how that works. It's exactly what I said was going to happen. So 60.35 divided by 3.14 comes out to be about 19.22 meters per second. So adding that over here, 19.22. And up here as well. The reason why these two are the same is because, again, acceleration is 0, meaning no change. Now, at this point, our table is actually filled out already. Okay? If I only wanted the individual components, I'd be done here. But I don't just want the individual components. No, I'm greedy. I want to know the actual speed that Tom Brady threw this ball at, and I want to know the angle. In order to do that, we need to do a little bit of trig. So, let's erase the board again. Okay, write what you need to write while keeping up our table. Okay, so we're going to erase our diagram here, kind of showing us what was happening. And instead, what we're going to do is we're going to actually draw out our vector. So I know Tom Brady threw this ball up at an angle, probably something like this. I don't know the value of my resultant vector yet. What I do know are the values of my x component. Okay, x is 19.22 meters per second. And my y component, 15.386 meters per second. Again, I still don't know this angle theta either. Okay, so my goal right now, what is r? What is theta? Okay, and here I'm going to rely on a little bit of trigonometry. See, whenever I have my x and y components and I want to find my resultant vector, I can use Pythagorean theorem. R squared equals x squared plus y squared. I have x, I have y, I can solve for r. So let's go ahead and do that. So r squared, our unknown, equals x squared, that's 19.22 squared, plus y squared, 15.386 squared. Now, in my calculator, I'm going to simplify those numbers out. So that 19.22 squared comes out to be about 369.4, give or take. And that 15.386 squared comes out to be about 236.73. So let me write those down. Okay, and we're going to write these in black now because these are no longer just the x and y values. So r squared equals 369.4 plus 236.73. In my calculator, I'll add those two numbers together. Okay, simplify the expression. And mind you, I'm using exact values in my calculator, so your numbers may come out a little bit different. I'm left with r squared equals 606.13. Now, at this point, it is important to realize I'm not done yet. I have r squared equals a number. I want r equals a number. So I have to undo that square. And the way that I do that is by taking the square root of both sides. When I do all that, I am left with r, my resultant vector, equals 24.62 meters per second, which is pretty fast. So that replaces my r here, 24.62. And that is my actual resultant vector. Okay, so for part B, when it asks me how fast does Tom Brady throw this pass, that is how fast Tom Brady throws this pass. But again, I'm not done yet. See, I still have to answer part C, the angle. Thankfully, I can keep on using a little bit of trig. Okay, so I'm going to erase this. Now, in math classes, you're taught a phrase called SOHCAHTOA, right? Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. In this case, the diagonal line here is our hypotenuse. Opposite would be our y-axis here. Adjacent would be our x-axis. So according to SOHCAHTOA, we should use tangent to solve for theta. Now, in order to actually get the angle, I need to use inverse tangent though. So, skipping all the actual trigonometry and everything, I'll save a trigonometry teacher to do that. For physics, we just kind of give you the formula here. Theta equals inverse tangent of opposite, which is y, divided by adjacent, which is x. Now, all inverse tangent is a function in your calculator. You hit the button, it gives you a number. So don't get freaked out by the fact that it looks like this weird math thing, okay? So, writing this out, plugging in our values in, theta equals tangent -1 times a y value of 15.386 divided by 19.22. So let's go ahead and do that in our calculator. So I'm going to start off by doing 15.386 divided by 19.22. When I do that, I get about 0.8. Okay, more exactly 0.8005, give or take. Okay, so I'm now left with theta equals inverse tangent of 0.8005. Finally, I do inverse tangent of this. It is very important at this point that your calculator is in degrees mode, not radians mode. If it is in radians mode, you will get the wrong answer. So I'm going to go ahead and I'm going to do second tangent. Okay, that's how I get inverse tangent of this, and I get an angle of 38.68 degrees. Meaning that my angle that Tom Brady threw this pass at is 38.68 degrees. And this sums everything up right there. That is basically our answer. Now, it is worth noting, the ideal angle to throw anything is 45 degrees. Okay, that is how you maximize distance. Maybe Tom Brady could have thrown a slightly better pass. Okay, who knows? Right, this is back in 2007. I was 5 when this happened. So, the long and short of this is that the Tom Brady problem, while my students may have found it terrifying, really isn't that different from a standard problem. It's just working in reverse. In physics, oftentimes you're going to be put into weird situations where you have to adapt. This is a form of adaptation. Being able to take the process that you're already familiar with and do it backwards. So, with that being said, as a little surprise for my students, by the way, if you are one of my Accelerators physics students and are watching this video before your midterm, this is your bonus problem on the exam. This is where your extra credit is going to be. Best of luck. Hopefully you watched this video, or hopefully you figured it out by now. That being said, make sure you absolutely demolish and smash that like button. Make sure you hit that subscribe button, ring the bell for notifications so you know whenever I upload a brand new physics video. Thank you again so much for 50 subscribers. It truly is mind-blowing that many people decided to subscribe to the channel, even if a lot of them are my students doing it as a joke. And as per usual, I will see you in the next video. Have a good one.